Hi, my name's Molly Hill, and today I'm going to be talking about a CFA interpolation method by Lukács and Platanidis based on normalized color ratio modeling. There are a variety of ways to capture color with a digital sensor. You can do it spatially, temporally, but the most common one for digital cameras, especially in DSLRs, is by using a color filter array. And then the most common of that would be the Bayer pattern, where 50% of the pixels are green, or rather allow green light through to the sensor, and then 25% are blue and red. You can see an example of a Bayer pattern in the background of the image to the right. Now there are different patterns available, but the only way they vary is which order the pixels are in a 2 by 2 pixel section. There's always going to be 50% green pixels, and this is because green is the most important to the human sensation of sharpness and luminance due to the V lambda curve. However, this means that the image has to be interpolated. There's no green data at a pixel that only allows blue light through, nor is there red information. The interpolation methods vary and continue to develop and will be addressed later in this presentation. When a DSLR camera is in RAW mode, it's outputting an image with this Bayer pattern yet to be interpolated. This means that the image isn't color yet. It's going to be grayscale. Here are some examples of what RAW images might look like before interpolation. Now, each camera does have its own proprietary RAW image format, such as DNG and CR2, but they're essentially the same. You can see that they're grayscale before interpolation, and in fact there are artifacts of pixelation that you can see in the close-up image on the right. It's not actually pixelation in the normal compression sense of the word, but rather, let's say you have a green object, then the green pixels will be bright and white in the grayscale image, and then the blue and the red will be dark, so you have this textured grid pattern that appears. So before, when I mentioned that a Bayer pattern could have different arrangements of the pixels but still be Bayer, those patterns would be like GBRG, GRBG, RGGB, and these are some examples of what happens when the pattern is incorrect. So when interpolating, it's important to find out and figure out which pattern your source camera uses. Although, given results like these, it's fairly easy to figure out. Two of the most common interpolation methods are bilinear and LaRoche and Prescott interpolation. Bilinear is a simple enough approach that averages the values of the surrounding pixels. However, this doesn't take into effect the content, so it can negatively affect sharpness, as it acts as a bit of a blur filter. On the other hand, LaRoche and Prescott does take into account uniform areas versus edges. Additionally, it uses more information, sampling luminance and chrominance, in an additive manner. In general, these two methods tend to have similar color outputs, but bilinear doesn't interpolate edges nearly as well as LaRoche and Prescott's method. Bilinear does have the advantage of being simpler and faster to implement. The main method that we'll be discussing today by Lukács, and I'm just going to call it normalized color ratio for now, or the normalized method. It's similar to LaRoche, but instead of a color difference metric, it's based on color ratio to the green channel. This method also allows for a field of weight values for edge detection, which you can create with a Sobel operator or some other form of gradient. The equation for finding the weight of an area is in the bottom right-hand corner, and you'll see where that W prime comes into effect in the next few slides. In my implementation, I tried doing different gradients, but ended up just using a field of ones just to get started, so it can be upgraded later. The paper also discussed how you can upgrade your implementation in a sort of way by fine-tuning your color with scaling and shifting, but this is also something that wasn't implemented this time around. The first step for the normalized method is simple bilinear green interpolation, and the equation you see in the middle doesn't quite look like bilinear, but that's because the averaging part comes in with the weight field that you saw in the previous slide with W prime. So at the end of this first step, you should have a green value for every single pixel in your image. Now it's time to interpolate for the red and blue channels. It's a very similar equation to the one you saw in the previous slide, but this time at each pixel location you divide by the green value, whether interpolated or not, that you found in the previous step. And then at the end of all of this, and it's all summed up and then divided to be normalized through the w prime value, you multiply the green value back in. This has to be done in 2 steps because only 25% of the sensor is made up of red pixels or blue pixels. So here's how you interpolate with the normalized method for step 1, and now step 2, and you should have values for every pixel location for all 3 channels. Now we're going to take a look at how these methods compare to each other in the results. We're going to be using 3 different image comparison methods. Delta E is a color difference metric in Euclidean space, and it can be done to a whole image or just per pixel comparing 2 different colors. And we're looking for a lower delta E for a better image. And better image in this case means more similar colors to the original. We're also going to be using peak signal to noise ratio, or PSNR, which measures the peak errors and their magnitude and how they differ between images. So we're looking for a higher PSNR in this case for a higher similarity. The third and final method is root mean squared error, which is used when you have a whole data set and want to see how much it varies within. So RMSE is going to be a metric that shows you how different the images are overall in a cumulative sense. So we're looking for a lower RMSE in this case for a higher similarity. I used 2 sample images for this project. One, a simulated image of different colors and patches and real-life scenarios, as well as fine lines and thick lines to test how it deals with edges. And I also used this image of a cat outside that I found on wesaturate.com. So for delta E, we're looking for a lower number for a higher similarity. Here you can see that LaRoche and Prescott versus bilinear has the lowest number of all. That's because they produce very similar color results. However, the original image compared to the 3 methods, bilinear and LaRoche are quite high compared to our new normalized color ratio model, which shows that, at least through the delta E metric, they should produce very similar colors. For PSNR, you're looking for a higher number, and for RMSE, you're looking for a lower. And once again, that shows that our new model should be the most accurate in terms of color. It's always good to put more than one image through a comparison test like this, so we put the cat image through as well. And the delta E was even lower between the bilinear and LaRoche methods. And once again, the normalized color ratio model was the lowest delta E compared to the original, meaning that it was the closest in color reproduction. The results are consistent for the cat image for PSNR and RMSE, with bilinear and LaRoche being very similar to each other, and the normalized model being, at least mathematically, the most similar to the original, especially with RMSE. Those numbers are absolutely astoundingly different. Here's just a quick look at the overall original test image versus the bilinear results. The first thing you notice is that the bilinear image is a bit darker, and I only showed that one in this case because, like we determined before, bilinear and LaRoche are going to be very similar. Here's a close-up of the test image. Now, on the right-hand side, you can see the colors are all very similar, but once again, all of the interpolated methods are slightly darker. You can especially see this in the skin tone and the pinks on the bracelet. It's very slight in these images, but you can also tell that the bilinear method doesn't have as much detail in those bracelets braiding as the LaRoche normalized and original do. What stands out the most in these detailed shots are the black and white bars, and as they increase in frequency, you see more and more color artifacts. LaRoche and Prescott, because of that edge detection that we talked about, so to speak, tends to have really good results, and you only see a bit of red at the highest frequency. Bilinear has a bit more, but normalized without implementing edge detection has a lot. Once again, this is something that could be improved in future implementations, but overall, as we showed with delta E, PSNR, and RMSE, the colors should be more similar to the original, even if the edge detection fails. Here are 2 images showing the delta E at each pixel location compared between LaRoche and bilinear. On the left is the cat image, which doesn't have a lot of hard edges, so there's almost no difference. But on the right, you can see that the colors are pretty much the same except for those high frequency edges in the test image. Here are the delta E images comparing the original image to each method. So on the left, we have the delta E between the original and LaRoche, and on the right, between the original and normalized. You can see that there's a lot of difference in the LaRoche method, but the high frequency black and white bars down the middle and on the bottom of the image are pretty much black, meaning that there's just about no difference when it comes to luminance. On the right, most of the image is black, meaning that the colors are very similar, if not the same or close to that, between the original and the normalized interpolated image. However, you see these white outlines on the high frequency parts showing that the edge interpolation isn't too great. Here's another example of the same comparison, except with different images, where you can see how the normalized is better at overall color matching. You can see some slight edge details on the right-hand image, but the cat image doesn't really have high frequency edges like the test image does. Overall, this was a decently easy method to implement, but I'm not entirely sure what went wrong in some areas. So the magenta part of the gradient up top, as you can see here, just kind of went black and dark with a sharp cutoff. However, the same color was perfectly fine in the patches on the lower right of this sample, except once again in the dark areas. So I'm not entirely sure what went wrong there, but it was an issue that presented itself. I also did try for a long time to get the edge detection implementation working. I tried Sobel operator and Laplacian filter, but there seemed to be some sort of thresholding issue with the image format that I'm not entirely sure how to work out. So here are some of the worst outcomes out of my whole folder full of them, but I was able to get it to a decent level, except for some noise in the uniform areas. So it's close, but you can also see in those high frequency bar patterns that the edge interpolation doesn't seem to be getting much better. So that would require further investigation in future implementations. Overall, the normalized color ratio model seems to be a successful CFA interpolation method in terms of color similarities. However, more work needs to be done investigating the edge detection and potentially the upgrade in the implementation for linear shifting and scaling.